皆さんこんにちは、エヴァンです。Vue Fes Japan に来られて本当に嬉しいです。久しぶりに日本の Vue コミュニティの皆さんと直接会えてめちゃくちゃワクワクしてます。今日は Vue と Vite のエコシステムの最新アップデートについてお話しします。ただ、まだ日本語で発表できるほど上手じゃないので、このセッションは英語でやらせていただきます。Okay, so, some quick Vue updates. So, in the last year, if we check the stats from October 13th, 2024, we were at 5.31 million weekly downloads, and just last week we're at 6.77. Actually, we were like over 7 million for a bit, but dipped down a little bit. There's fluctuations, but overall, Vue saw 27.5% growth in the past year. So I would say that's pretty decent because Vue is already 11 years old, and so we're still growing. Vue 3 now constitutes 77.6% of total NPM usage, up from 66% last year. So that is actually also good news because it shows that the ecosystem has caught up. Almost all the new projects are now exclusively using Vue 3. So some future work. A lot of you probably know that Vue 3.6 is already in alpha, and we're actually going to beta very, very soon. Most of the beta changes have already been merged into the minor branch. So 3.6 is mostly focused on internal improvements. So I consider Vue a very stable and mature framework at this point. So, and also because of the Vue 2 to Vue 3 transition. So our main focus for the foreseeable future for Vue is really stability and making sure the ecosystem can have a very stable foundation to build on top of. But with stability, we also want to keep improving the framework from the inside out, which means we are constantly trying to re-implement the internals to have better performance without changing the API. So the first thing in Vue 3.6 is that it will be powered by alien signals. There will be a talk about alien signals later today about its details, but essentially alien signals is the reactivity engine inside Vue. It is the system that allows Vue to track the changes, track where the data is used, and automatically trigger updates when things change. So alien signals is made by Johnson, Vue core team member, and in fact, signals as a paradigm has been widely adopted across different frameworks, including Svelte 5, Solid.js, and many other. So alien signals is literally the fastest signals implementation in JavaScript and has been ported into Vue 3.6 to be the new reactivity engine for Vue. And then there is Vapor Mode. We have been talking about Vapor Mode for a very long time, but just in case for those who are not familiar with it, Vapor Mode is a new opt-in compilation strategy for extreme performance. From the architecture diagram, you can see this is we are able to implement Vapor Mode without affecting any of the existing code because of how Vue's internals is architectured, right? So we have the base compiler core and runtime core well abstracted so that we can add compiler vapor and runtime vapor without inducing major changes in other parts of the framework. This also means when Vapor Mode lands, you are able to progressively adopt it in part of your application without having to do a full rewrite. But at the same time, Vapor Mode is focused on compatibility, which means any API that exists in both Vapor Mode and normal Vue, they will behave the same. right? So you can, in a lot of cases, you will be able to take your existing Vue single file component written with script setup, and it will just work as a Vapor component. So the idea is exact same API, right? So this is a typical Vue single file component, and Vapor mode will output different compilation output. This, on the top, is the current virtual DOM-based compiler output. And this at the bottom is Vapor-based compiler output. From the end user, the behavior of this component will be exactly the same, but it will ship slightly less JavaScript, it will be more memory efficient, and it will be much more performant. So Vapor mode progress. Vapor mode is taking a long time because we need to ensure it actually has feature parity with the rest of the, we have a lot of features in Vue, so we need to make sure Vapor mode covers all of the features that we would use day to day. So some of the most challenging ones are the built-in components, which are really advanced use cases. So keep alive, teleport, transition, async component, scoped styles in single file components, all of these need to have dedicated implementation in Vapor mode. And most importantly, hydration for server-side rendered applications. This is probably the one that's taking the most time, but we have finally reached a point where we are able to run VitePress, the default theme, with Vapor mode, and everything hydrates and works correctly. So in terms of performance, this is the latest benchmark screenshot I took from this morning. In the JS framework benchmark, Vue Vapor mode is outperforming Svelte 5, outperforming Solid.js. It is now the fastest mainstream framework that you can get on the market. So we expect to release a beta for 3.6 before end of year. So if you're interested, keep an eye on the minor branch on GitHub. That's where most of the action is happening. Yeah, so that is pretty much what we are planning for Vue 3.6. And so now, oh, right. So outside of Vue core, one important thing I want to mention is Vue language tools released 3.0 earlier this year. Many of you probably, because it auto upgrades, right? So you probably don't realize you're using it, but the important thing is hybrid mode is now always on. It has major stability improvements. I believe this is important for the developer experience for Vue users. And also, we worked with Johnson to essentially support the project so that the insider version is now made free for everyone. So all the advanced features that were previously in the insider program are now freely available to everyone. And Johnson will also talk about, have a talk about the 5 years of how Vue language tools evolved over the years. The IDE support in language tools is a very, very complicated task. I would say even the complexity level is probably the same as the core itself. So it's a talk that definitely worth listening to. Okay, so now let's talk about Vite and Voice 0. So Voice 0, for those of you who don't know, we are a company that builds build tools for JavaScript. So we make build tools. But why does JavaScript need build tools in the first place, right? Because everyone here are probably JavaScript and web developers, so you know what build tools are for. But when I go out and meet people who don't work in the field, I tell them, hey, like they ask me, what do you do? I'm like, I run a company that builds build tools for JavaScript. And if they're not a front-end developer, they will ask me, like, why does JavaScript even need build tools? Doesn't it just run in the browser, right? So oftentimes I have to like go back all the way in the history of web development and tell them how did we arrive here? Well, the reason is JavaScript was invented as a scripting language. When Brendan Eich, the author of JavaScript, created language, he did it in 10 days. He did not foresee that the language will be used for the kind of applications we're building today. Today, we're building more and more complex, more and more ambitious applications on the web. We deliver them directly in the browser, right? That's an amazing feat. But the scale of these applications are growing so fast, we run into all kinds of challenges. And if you're an engineer, you know, when you scale things up, there's bound to be new problems, right? So we organically discover these problems as we are trying to scale things up, right? So your files start getting too large. Now you need to break them into individual modules. You want to ship reusable code. You want to share it between teams. You want to share it with other people, right? Then we need a package registry and package managers. You can't just have thousands of modules and load them directly over HTTP because that will be too slow. There are too many network requests. So we need to reduce the number of requests, so we need bundling. There's new custom syntax, right? When ES 2015 came out, all the browsers did not support the new features, so people invented Babel compilers to transform our new syntax into code that the browsers today can understand. Your files get too large, right? You want to deliver, you want your website to load faster, you need to minify things. You want to make sure it works, you need test runners, linters, type checkers. You want to make sure your code looks consistent. You want a big team to write the same style of code. You need formatters. And eventually, builds get so large and complex, it's taking minutes and minutes to build. So people started using test runners and caching systems, right? Monorepos with monorepo caching runners. So in trying to solve these problems, people started writing different tools. And the first batch of build tools written for JavaScript were written in JavaScript itself. So I call these tools written in JS for JS, right? So there's Babel, Acorn, Esprima. If you've been involved in the early days of JavaScript tooling, you probably are familiar with some of these names, but some of these are probably also lesser known if you're newer in the field, right? So all of these things are written in JavaScript. They worked great when they first came out. Thanks to Node.js, JavaScript developers finally are able to write their own tools in their own language. However, as things start to scale, as I said, performance becomes a real issue, right? If you have worked on a Webpack plus Babel plus Jest application that grew over time, you probably have experienced really, really slow startup times, really, really slow build times, and it gets to a point where it is really slowing you down in terms of your development experience and development workflow, right? So that's a real problem that we're facing. So the next generation of tools that emerged in the past 5 years or so, I call this the next gen. Actually, it's the current gen, I would say. These are tools written for JS, but in native languages, right? So there's SWC, Oxc, Biome, ESBuild, RSPack, TurboPack, etc., right? So some of these are written in Go, some of these are written in Zig, but most of them are written in Rust, right? So these are the major languages. There are different trade-offs between these languages, right? But in general, there are, I can go a bit deeper into the language trade-offs, but at Vue.0, we have chosen to work with Rust because that's what the team is most familiar with, and it's also the language we believe has a right balance of performance and strictness, and also good WebAssembly support. So how fast is native tools, right? So this is a general sort of ballpark number of how much faster it can be, right? People say you can make JavaScript fast, but only to a certain extent. JavaScript is fast compared to other scripting languages, but it is inherently single-threaded, and it is very difficult to fully parallelize JavaScript in its current form. But native languages are able to leverage multiple cores. It's closer to the metal. So the level of performance you can achieve with native languages is still significantly better than JavaScript tools, right? So we have seen amazing performance gains with these new generation of tools, but it's still fragmented, right? You still need to put together tons of different tools into a custom stack in order to get the latest. Also, people are getting tired of the churn because every 1 or 2 years, you're like, oh, this tool is deprecated. I need to move on to this new thing. And we keep doing that over the years, right? So the idea behind Voice Zero is we do want to see if it's possible for us to build a unified toolchain where we start from the ground zero. We start with the parser, then we build on top of the parser to build the transformer, to build the linter, the formatter, the minifier, and on top of these, we build the bundler, and on top of that, use that bundler to power Vite, use Vite to power Vitest, so that we can have a full toolchain coherently designed from the ground up, all using the same AST format and guaranteed to work together smoothly. So that is exactly what we've been doing in the past over a year and a half. Right? So what's new? We are seeing a great adoption of the tools that we're building. Vite is now at 36 million weekly downloads, and that is, we saw over 100% growth in the past year. Similarly for Vitest. Vitest is quickly replacing Jest in a lot of enterprise applications, and people are building additional tooling on top of Vitest. For example, there's someone, Matt Pollock is building Evalite, which is an AI eval test runner on top of Vitest. Right? There's Rolldown, the Rust-based bundler. It started as a port of Rollup, but we eventually evolved it into something that has the speed of ES build, the API surface of Rollup, but also the advanced power of Webpack. Right? So we want to build the bundler with the best of all the worlds. A year ago, Rolldown barely had any downloads because it wasn't even ready yet. But now we are actually seeing Rolldown in production in big scale companies, and it's the download number just like exploded. And Oxc itself, this is counting all the numbers of the lower level components in Oxc, including our parser, transformer, resolver, etc. Some companies that build really advanced JS infra, like Atlassian, they are using individual pieces from Oxc to power their custom JavaScript tooling infra, because Oxc really provides the level of performance that they have to that they're dealing with, and JavaScript-based tooling just doesn't cut it anymore. So Oxlint is the linter that is based on top of Oxc. It is designed to be a direct replacement of ESLint, but up to 50 to 100 times faster because it is written in Rust and is able to leverage all the cores. We have ported over 600 ESLint rules, and the number of rules are continue to grow. We also include experimental support for type-aware linting. This is an interesting topic in the linting world because in ESLint, you have to use TypeScript ESLint, which goes through TSC. But TSC, when it does type checking, is really slow, so it makes your already slow linting process even slower, and has become a major bottleneck. Some of the companies we talk to, their code base is so big that they simply cannot run type-aware linting at all because it just goes out of memory. Luckily, the TypeScript team is porting TypeScript itself to Go. So that is TSGo. So TSGo linked is essentially vendoring TSGo and building a linter, type-aware linting rules on top of it. We integrate TSGo linked inside Oxlint under the same reporting surface, same configuration surface. So you don't need to be aware that there is TSGo linked running inside Oxlint. You just use the same configuration, same rules. You just say enable type-aware, and you get the type-aware rules running for you. Now, the performance of TSGo linked is about 10 to 15 times better than TypeScript ESLint. That is still very slow compared to Oxlint itself. So Oxlint is able to link thousands of files in milliseconds. TSGo linked slows that down by maybe 8 to 10 times, which is still much faster than the current ESLint workflow, but we are working with the TS team, TypeScript team, and Microsoft to report issues and fix performance issues as we test them in larger code bases. And then Oxlint ships custom JS plugin support. This is important because there's so many custom ESLint plugins and rules in the world, in the wild, people rely on. And if we cannot support these rules, these custom rules, there's no way that we can get the whole ecosystem move over. So this has been something we've been investing a lot into as well. And I'll talk a bit about the technical details a bit later. And then there's OX format. This is the prettier compatible formatter built on top of OXC as well. It is now in alpha status. It's actually already published on NPM, and you can try it out. The test conformance with prettier is at 92% and increasing. Performance-wise, it's 2 to 3 times than Biome, which is also written in Rust, and 45 times faster than prettier. Some of the things we want to do, instead of just being a strict prettier port, is we're adding some more flexibility in terms of line wrapping options. Because one of the major issues many people have with prettier is how strict it is when it comes to wrapping lines. So we have an RFC internally, and I believe we're going to provide a good middle ground for people who want to use prettier but hate the line wrapping behavior. So OX format also covers the stylistic and sorting features. For example, import sorting, Tailwind CSS, class sorting, etc. So anything that's related to making your code look good, it goes into OX format. Right now, OX format has limited support for other file extensions other than JS and TS, but in the short term, we're supporting it through Prettier's own plugin system. And we'll gradually port those additional things to Rust as well. Okay, so for Rolldown. Rolldown, like I said, a year ago, Rolldown was not even ready. But in the past year or so, we shipped more features, made it more stable, but also made it even faster. It is now consistently faster than ES-Build. We actually just recently had someone replace their whole AWS Lambda build migrated from ES-Build to Rolldown and see double the performance gains on a multi-core setup. We are also 3 times faster than RSPack, which is also written in Rust. We also shipped major bundle size improvements to get much closer to state of art in terms of minification, tree shaking, and optimizing the output. Framer, the company that builds a website building service, they switched to Rolldown from ES-Build, and is now using Rolldown to bundle 100% of their customer websites in production. We have collaborated with them in depth over the past year. So a lot of the feature requests and stability issues we have verified with production workload. It is also now being experimentally used in Angular build. So the next version of Angular may be using Rolldown for additional chunk optimization. So this is a comparison. December 2024, the first beta release of Rolldown versus the latest one. Well, this is not the latest one. We just released a few new versions, but the number here is over the less than a year, right? We got Rolldown to be 33% faster, and it produces 34.5% smaller bundles, right? So it just keeps getting better and better. And we're not going to make it slower just because we're shipping more features. We are actually constantly optimizing the performance. Okay, so for Vite itself, the last major version of Vite, 7.0, it is a relatively small update. So it is mostly adjusting the node and browser support range updates. The other major thing is probably official React Server component support in the form of a plugin. So Hiroshi worked on it, and if you're interested in React Server components, you should check it out. But mostly 7.0 is a preparation step for the big thing that's coming later. For Vitest, we just released Vitest 4, I think this week. So browser mode is now stable. Browser mode allows you to write the same unit tests for your components, or transformed with the same Vite configuration, but they run in actual browsers through Playwright. So you get more closer to real environment test results for your interaction tests. The Vitest also now ships with visual regression testing, and the next quarter's focus will be improving performance. Okay, now, Rolldown Vite, right? The whole reason we were building Rolldown is to get it into Vite. We wanted to power Vite, and we are actually approaching full compatibility, right? In order for Rolldown to fully power Vite, we do have some extra work to do on top of just the bundler because Vite has its own special logic that were previously all implemented as rollup plugins, right? In order to make the whole system fast, we ported most of these internal Vite plugins to Rust as well, right? And now in Rolldown Vite, they are enabled by default. With Rolldown Vite, we are seeing up to 20 times faster production builds compared to today's Vite. And we are shipping this soon as Vite 8 beta. And we plan to ship fully Rolldown powered Vite as Vite 8 in early 2026. Another important feature that's coming in Vite 8 is full bundle mode. So this is currently still experimental. We just got it working and we're seeing preliminary results. So this is from a synthetic benchmark where we're just loading 10,000 React components. Right? Your app is probably not that big, but if you have worked with Vite on a really large application, you probably have experienced a really slow time when you first start the dev server and trying to open the page. You just see it spins and waiting for it to load. So that is a fundamental limitation of the unbundled dev server that Vite ships by default. And full bundle mode is essentially going back to bundling it because now we have a much faster bundler that is able to handle both the dependencies and your code really fast. So with full bundle mode, we're able to reduce the server startup page load time by 15 times, and reloading the page can get 10 times faster. And we're now testing this with Linear, which is a full Vite application, trying to improve their development experience as well. Okay, so we are seeing amazing performance gains, right? When we claim the numbers like 50 to 100 times faster linting, 20 times faster builds, all of these are comparing the current status with pure Rust applications, right? But Rust is fast, but JavaScript developers like writing plugins in JS, including frameworks like Vue or Svelte, right? The framework compilers are still also in JavaScript. So there's also many ES-linked custom plugins rules. React compiler is also still in JavaScript, right? So when you add these JavaScript-based transforms into a Rust build toolchain, it slows things down drastically, right? It kills the performance. So what can we do? Well, maybe we can rewrite everything in Rust. Well, that's probably not feasible. So we got to find some other ways. So the answer is we need to make JavaScript plugins fast, right? So what can we do? We spend quite a lot of effort in trying to figure out what to do in this front. So on the first thing is we noticed that a lot of the custom plugins, especially transform plugins, they're doing additional parsing in JavaScript, right? For example, we have a Rust bundler. The Rust bundler has already parsed your code. It has the AST, but when you're trying to do a transform plugin, you use a JavaScript parser to parse the code again, right? That's very wasteful. How can we avoid that? So the first idea is you want to pass the AST that already exists on the Rust side to the JS side. Turns out that's slow too. This is why we worked on a thing called the raw transfer for AST. AST raw transfer in Oxc. So what does it mean? So here's an example, right? The yellow bar is parsing a JavaScript file in Babel. The orange here is parsing with Oxc. So Oxc itself is close to 19, 20 times faster than Babel. However, the moment you try to send the AST from Rust to JS, it becomes almost the same speed. Just the cost of cloning the data in memory and then sending it across the Rust and JS boundary is extremely expensive, right? So it makes the whole thing 14 times slower. So one thing we did in Oxc, thanks to the design where, because in Rust, the AST on the Rust side is held in a consecutive chunk of memory called an arena allocator. We're able to just take that chunk of memory and send it directly to JS without cloning using a shared array buffer. Now, so when you get the memory on the JS side, you still need to turn them into JavaScript objects. So that step is called deserialization. Right? So in JavaScript, we need to deserialize the memory into JavaScript objects so the plugin can work with it. Turns out the transfer itself is now free, but deserialization still costs a lot of time. And there's also the garbage collector, because you're allocating a lot of small AST nodes, which you probably don't end up even using. So they need to be garbage collected. And that makes things slow too. So what can we do now? So when we are implementing the linter rules, we notice that we don't really need to access every single AST node. For example, if you're implementing a node debugger linter rule, you only really care about debugger statements. So what if you can ignore everything else and only instantiate the AST nodes for the debugger statement? So this is what we call lazy deserialization. This is what we have a prototype that's working. It's not fully implemented, but this is the result of actually implementing that. We're able to get it down to probably only double the overhead compared to raw Oxc parsing. So this is important because we are able to leverage this whole mechanism, raw transfer plus lazy deserialization, for both linked plugins and transform plugins, right? So in Rolldown, we are shipping a new transform hook called Fast Magic String Transform. So the idea here is inside a Vue plugin's transform hook, you can now receive the AST directly for the current file with lazy deserialization. On top of that, you can now use a magic string API to manipulate the code. I don't know how many of you have written a Vue plugin yourself with magic string, but the idea here is magic string is a very popular JavaScript utility that allows you to take a piece of JavaScript code and then start just like manipulating it. You can change some text, append things, move things around, right? And eventually you can just generate a new string and generate the source map for those changes. So this is very, very commonly used in Vue plugins. In fact, some framework code also does this too. We want to make this fast, right? The reason this is slow right now, by the way, this is already much, much faster than a full Babel transform. Babel is even slower than this, right? Magic string, right now, you need to get the code string from Rust. You need to parse the AST, traverse the AST, call the methods. You generate the final string and source map on the JS side. And eventually you pass the string and source map back to Rust. So all the middle steps happens on the JavaScript side. That's why it's slow. We want to move as much work from JS to Rust as possible. So this is after the fast magic string transform. We will get the raw AST from Rust. That's much faster now. On the JS side, we lazy traverse the AST. You only visit the nodes that you are interested in. And then you call the magic string methods. Calling these methods are extremely cheap, right? Because they don't actually do anything at the moment you call them. We buffer these method calls and only send the method calls and their arguments back to Rust. So minimize the data that we need to send back. And eventually, we let the Rust handle the final string generation and source map generation, right? So now we move the bulk of the work from JS back to Rust. And we also minimize the transfer cost between the two language boundaries. This is how we make transforms fast in a Rust-based bundler. And if you are writing a custom transform plugin for Vite, we really encourage you to look into this and migrate over once Vite 8 is out. Okay, so the final question, what are we building on top of all of this, right? We are shipping a lot of open source. We're doing all of these different projects. So what about the unified toolchain vision we talked about when we started the company? So this, on the right side, all the stuff we've been building, supporting all the frameworks. On the left side, this is what we are turning it into. It's called Vue+. It is a unified toolchain for web and JavaScript. We do have a website up at vueplus.dev. So we announced this in the past week, Some of you have probably seen my talk at ViteConf in Amsterdam. We also published a blog post talking about this in more details. So definitely check the information out if you're curious. But at the high level, Vite Plus is a toolchain. It is a drop-in replacement for Vite itself. So if you have a Vite application today, aliasing it to Vite Plus, your application will continue to work exactly the same way, except you now get access to additional commands, including Vite lint, Vite format, Vite test, Vite lib, Vite new, Vite run, Vite install, Vite UI. So I don't have time to go into the full details of every single of these, but I hope they are self-explanatory if you have worked with configuring your own set of dependencies, right? So the nice thing about this is a single dependency for all of these things. So the next step for Vite Plus is we also want to expand the capabilities of plugins, right? So just like Vite Plus itself is a superset of Vite, Vite Plus plugins are also superset of Vite plugins. So today's Vite plugin plugs into Vite and can say, inject transform hooks or mostly about build, right? So Vite Plus plugins will be able to inject, for example, custom generators, scaffolders, custom test environments, or test assert matchers. You can inject your own lint rules, right? So the plugin will get access to more aspects of the toolchain. And also, there is this trend of frameworks shipping as Vite plugins. For example, 10-stack start, StyleKit. These are frameworks, but they actually come as Vite plugins, right? So theoretically, with Vite Plus, these frameworks as a plugin can now also ship their own additional framework-specific extensions to other commands in the toolchain. In the long run, we are also thinking about how a unified toolchain can play better with AI, because we're now seeing more and more developers using AI agents and AI assistant code tools to work with these development tools. So we believe agents and tool go hand in hand, right? Agents need good assistance from the tooling layer. So a unified toolchain makes it easier for the agent to understand how to work with it, because we can have centralized documentation. We can have default recommended prompts for you to put into your agent instructions. When we notice that you're working with an agent, we can have these small fine tweaks in development experience to make it work with agents. For example, we are working on forwarding browser runtime errors into the console. We're working on things like optimizing the output for agents so that it's optimized for agents to accurately understand what's going on instead of optimized for human readability. We also want to improve this, the overall goal of agent mode is to improve the speed, accuracy, and token efficiency when you're using Vite Plus with AI assistance. So finally, Vite Plus is going to have a pricing element involved, right? Because we are a company and we want to make sustainable open source. Right? Vite Plus is powered by the online open source projects. Now, everything that is open source today, Vite, Vitess, Rolldown, Oxc, they remain MIT licensed and open source forever. You keep using them, don't worry about it at all. Vite Plus is completely new. So right now this is preliminary plans, but we will announce more details about the pricing later. You can also check out the website and the blog post to learn more. Okay, so that's it. Thank you very much.